Okay, for today's class activities, we're going to cover Chapter 10, Sections 4 through 5. Make sure you read those thoroughly to get an introduction to the concepts, and then we're going to look at concept questions 8 and 9 and exercises 25 and 51. So go give those a try, and then come back and we'll step through them, starting with number 8. Okay, so number 8 is an example of an energy diagram. And it's got a few really good questions. So I'll redraw it out here. We have it basically, I'm trying to draw it kind of carefully here. We have the potential energy curve, looking like this. The text likes to do PE on the diagrams, and I like to do U, but I'll go ahead and stick with the diagram as labeled in the text. So this is a potential energy curve. And then they also show that there's a total energy curve. That's like this. Okay. Now the question is to try and interpret this graph in terms of what the particle is doing. We are told that about right here, which is about at 5, about right here, the particle is starting right there, but has this total energy. Okay. Now, before we start answering the other questions, let's try and describe what's happening right at this point. What's the particle doing? Is the particle moving? The answer is yes, because it currently, at this position, it has this much potential energy, but there's this much total energy in the system, which means the kinetic energy is the difference between the two, or that much kinetic energy. So it is moving, and we were told it is moving to the right. Okay, but the biggest idea is that you can find the amount of kinetic energy based on the difference between the total and the potential. Okay, so the first question is, at what point or points is the kinetic energy or the speed maximum? Okay, so how would you find that out? Okay, so wherever the potential energy is a minimum, that means the speed is a maximum. And that is right here, which is at 0.6 off the graph. So here is the lowest spot in the potential energy, which means the particle gains its greatest kinetic energy and therefore its greatest speed at that spot. Okay, well, what about turning points? How do you find a turning point off of an energy graph? Okay, so a turning point is where the particle turns around, which necessitates its velocity to be 0. Well, where is the velocity 0, or in other words, the kinetic energy 0 on this graph? It's where the potential energy equals the total energy. Okay, so at this point right here, which is at 2, and at this point right here, which is at 8, that is where the kinetic energy is 0, and therefore the particle's velocity is 0. And given that it has motion in between, that means it's a turning point. So it will have a speed moving to the right here, move fast, slow down, stop, come back this way, speeding up, slowing down a little bit, but still going, speeding up, and then slowing down until it stops, coming back this way. And so it'll oscillate between 2 and 8 if there's no loss of energy. It'll oscillate between 2 and 8. Turning at those 2 points, because that's where the potential energy equals the total energy, which means the kinetic energy must be 0. Okay, so if we could change this total energy, maybe make it bigger, increase the total energy or decrease the total energy, could we make the particle stay at rest? Could we put the particle at rest? What would that mean? Okay, so if the particle's at rest, it means it's not going to move. All right. So thinking about spots, you could place this, positions, you can place this object so it wouldn't move. It means that if at that point it had no kinetic energy, or in other words, the total energy touched that spot on the potential energy graph, it would not move from that point. Okay, so for example, if I look at this point 5, if I drew the total energy through this point right here, so that means there's no kinetic, would the particle not move? The answer is no, it'd still move, because even though it start at rest, okay, it would then speed up, because it now, by moving a little bit towards larger x, larger position, it's going to gain kinetic energy by losing potential. So not here, but if I started it here, or in other words, had my potential, my total energy right there, that means it has that much potential and it's not going anywhere, because if it went this way, it would have more potential energy than it has total energy, and therefore it has to have negative kinetic energy, which cannot happen. Same would go for moving to the left. And so this would be a point of equilibrium, and particularly stable equilibrium. Okay, so if we lowered the total energy to this level here, then we could hold that particle at rest. Now we could also do that at here. This is called a local minimum. It is small with regards to its closest surroundings. Okay, and the same thing, if we put the total energy at this point, then even though if it was over here it could move, it's constrained, because it's still, in order to get over there, it's got to go up. It's got to get up over this hill, then can go down. And so if the total energy is right here, then it has no kinetic, it's at rest, and is again constrained to stay there. Okay? And I like this. This is an example of enzyme kinematics, and in the sense that what an enzyme does is it helps a reaction occur by giving it just enough energy to get over a small bump, so that it can then put out a lot of energy. Okay, and so you can model some chemical interactions via diagrams like this. Now there's one more spot I want to point out. What if we lowered the total energy to be right there at the top there? Okay, so if I have a particle at this position and the total energy is there, so that means it's not moving to start, would it move if I let it go? And this is a tricky one. We call this a point of unstable equilibrium. If you could place it there and truly have it have no kinetic energy, if it's at that perfect peak there, it would have no preference to go left or right, which means it wouldn't go left or right. It wouldn't go either direction. But if you just blew on it just a little bit, gave it just a little bit of kinetic energy, then it would move away and move away fast. So these points are points of stable equilibrium. Okay? They can't go away from them. This one could go away from here, because its potential energy gets lower away from it. So these graphs like this are a really powerful way of analyzing a lot of different physical systems. Okay, let's move on to number 9. Okay, we have a block up an incline, a compressed spring. It's going to shoot it up that incline. And the question is, what would be the best choice of a system so as to analyze this in the simplest way? What do you think? We've got a spring, we've got a block, we've got an incline, we've got the earth. What would be the best system to analyze this? I'm going to propose that the best system, even though you can pick different systems, you can get the right answer in the end. I'm going to propose that the best system, to make this the easiest problem, is to include everything. If I include everything, if my system is everything, the spring, the block, the incline, the earth through gravity, then I don't care about the acceleration of this block as it moves up the hill. I don't care about the fact that the force of gravity is straight down and this motion is up that angle. I don't care about any of that. All I care about is what energy is in this beginning spot and what energy is in this final spot. And if I include the earth, then that's a gravitational potential energy, and I know how to do that one. I include the spring, well, that's a spring potential energy, I know how to do that one. And then I just have kinetic energies. And so I could, by picking the whole, everything interacting as a system, then I can analyze this in a very simple way with just using conservation of energy. So system of everything allows me just to say K initial plus U initial, and we'd have UG initial plus US initial will equal K final plus UG final plus US final. And if we try and figure out how high up the block goes, well, that means it stops, so that would be 0. When it's up there, the spring's not stretched anymore, so we have no more up there. When it starts down here, we can choose a coordinate system, so that's 0. And it actually is at rest to start, while the spring is compressed at its maximum, it's at rest. So really all that happens is, say, spring potential energy got transformed into gravitational potential energy, which we could find that by how much it stretched and find out by how high up it went. Okay, very good. Let's move on to number 25. Exercise 25. Here's another energy diagram or energy graph. So try and apply what we did here to number 25. I'm going to draw it out, but go ahead and try and work on that. Okay, so we've got this potential energy curve as a function of position. These numbers here are in units of joules. Okay, and we're told that this particle is half a kilogram, 500 grams. And we're asking, what is the speed of this particle at points B, C, and D if it starts at point A with 0 speed? Starts at rest at point A. How are we going to use this graph to figure that out? So, by understanding that it starts at A with 0 speed, that means the total energy is equal to potential energy. And so, I can draw a line straight across, and that's my total energy, E total. All right? Well, what does the kinetic energy look like? Well, that means at A, the kinetic energy is 0, and what happens at B? Well, that's the difference between these two, so that's a difference of 3, so I'm going to be up here. What about at C? Well, it's a difference of these two, and that's a difference of 2, so I'm going to be right here. What about D? Well, it's a difference of 5, so there's no potential, so it's all kinetic. So I get something that looks like and I get a mirror image like we've been expecting. This is my kinetic energy. I get a mirror image. So I can say that K at B is equal to 3 joules. K at C is equal to 2 joules. And K at D is equal to 5 joules. And this was equal to UA minus UB. This was equal to UA minus UC, equal to UA minus UD. Okay. So we can do graphically, or we could have used conservation of energy, recognizing that my change in potential gave me my change in kinetic energy, with K initial or Ka being 0. All right. Now I'm going to do 51 in a different video. It's a bigger problem, and I want to spend a little bit more time on it and have it available separately.